Drew, if you could maybe pan up on this board, just some of the basic characteristics of a flow grid regulator. And I know you all probably are interested in this because you have them and you have to maintain them. So, flow grid regulator, basically, they're all carbon steel. So they're rated to 1,480 pounds. And so what determines what is the appropriate setting for a flow grid regulator is, and you can pan down on this now, is basically the connections. And so the bodies come from a 1-inch size, like this little 1-inch NPT FG11, up to a dual port 12-inch flow grid, like an FG80 is an example. You just basically decide then, based on what the size of the body needs to be and its connections and what ANSI class, helps you pick your model of the body. But they're all carbon steel rated to 1,480 pounds. The next thing about them is that they're, and by the way, speaking of connections, the connections have a lot of flexibility, at least up through 4-inch. So you have the ability to get flangeless in certain body sizes. You have the ability to get butt weld and socket weld options. There used to be, and there may be in some of your system, some smaller dual ports where you have 2 throttling areas, 2 control areas in the same body. Those had been discontinued in favor of the 10 and 12-inch, only having that configuration of a V-twin kind of throttling, but all the rest of them are single port. As far as outlet ranges, since they can work in pressure control applications, flow control applications, and also as reliefs, using a Mooney pilot, such as this one, we can basically set pressures downstream of between 3 pounds to, with a high pressure spacer added here, up to 900. And then if we use a low pressure pilot, 20L pilot, which I will show you here today, we can basically drop that outlet pressure down to 5 inches of water column. So that's the range that this thing can operate at. The bodies themselves can handle a differential pressure of 800 pounds if it's 2-inch and larger. When the body is like these with a 1-inch throttling area here, like this one, or the one that I had in my hand, the 1-inch throttling areas, they can handle a 1,000-pound differential. Obviously, I wouldn't put 1,000 pounds across this valve because it has ANSI 150 flanges. But if I had 600 class flanges on this, then I could put 1,000 pounds across it. So the only thing we have in our offering that is got a better, like normal differential pressure situation is the 900 top entry flex flows, 900 TE flex flows. They have a real heavy carbon steel casted body, and they can handle 1,200 PSID. So that's one of the reasons that we might move away from a flow grid if you really had that as a required component, like if the valve failed and it had to handle that kind of pressure. The next thing about it is the minimum differentials. The minimum differential of a flow grid is something that may have you like move to a flow max in a lot of instances because it needs a little bit of differential pressure to operate. You need to have about 20 pounds of pressure cut being made, or if it's going to be a relief, that the relief set point is going to be about 20 pounds so that the differential to atmosphere is that 20 PSID. And I'm not saying that the valve takes 20 pounds to open. What I'm saying is in order to ensure that it will lock up when it's supposed to lock up and perform well in that environment, it's always good to have a little bit of differential pressure between what's being put on top of the diaphragm to close the valve and what's trying to basically push up from the underside and open it. So, you know, you might have a little debris or wear and those kind of things. So having a little added differential pressure on top is always a good thing to make sure you're getting the best performance from the valve. So we don't really spec flow grids when you don't have a 20-pound cut. They will start to open in just, you know, a couple of pounds, but they're not going to go full open typically, depending again on the size of the body and that kind of thing. Between 8 and 12 pounds usually is what it takes to get the diaphragm fully lifted off the throttle plate and give you the full capacity of the valve. So if you're in a situation where you're needing a flow grid, there's things we can do. And let's say you're making a 15-pound cut. There are things we can do to make it perform well enough in that environment. But it's just not optimal. It's really getting into flow max range when you're making a shallow cut, or you have a lot of requirement for flow, you know, a large flow rate in the same body size. Those get
Hey,
into
Drew.
Yes.
Drew, are you presenting anything by any chance right now, or you're just talking for right now?
He's just sitting here with me.
Oh, but you're not presenting anything right now?
Jeff is. It's got the video up. Do you not see anything?
No, I only see a whole bunch of names. We don't see nothing on video. Unless the other guys, any other guys, can y'all see anything on there?
Oh man, I'm sorry. See, we
Yeah,
run into our first
Rudy.
major flaw.
Yeah, I can see, I can see it, Rudy. This is Rod. I can see him clear.
Okay, just want to make sure y'all can see it, because I can't see it. Just make sure that y'all are seeing it.
So if you will go to the top right of your screen, there's a little view button. Click
Okay.
view and either do speaker view or gallery view and double click on the image. It should be under Drew Brandt. That should make our video the whole screen.
Okay, got it. Thank you.
Then at the bottom of your screen, if you don't have audio, you can't talk to us. There's a little chat bubble. You can type questions or responses in there, and we will get them.
All right, thank you. Appreciate it.
You're welcome.
Anybody else having a problem we can get sorted out real quick? All right, we roll. Okay, so we talked about the maximum and the minimum differential pressure ranges. As far as the temperature ranges, and a lot of this is kind of being dictated by the soft goods that you put in. Most of the variant soft goods, as far as the durometer, is nitrile. They also have a Viton option. So under normal pressure ranges, you're talking about minus 20 to 150, with minus 40 and plus 175 is the range that you can basically go to during kind of non-standard situations. And if you put the Viton in, you can get up to 220. The challenge with the Viton is that it doesn't handle the cold as well, so you're losing some of that bottom end. It's kind of expensive as a soft good. It's not our standard. But it is a good one if you're experiencing a situation where, like, you have sour gas, you know, you are trying to get kind of a valve that is kind of as close to NACE compliant as can be. It's carbon steel body, so it's not going to be NACE, but the throttle plate stainless steel, the pilot can be stainless steel, all the other components can be stainless steel, and all the soft goods can be Viton. So it'll work pretty well in that environment. And then talking about turn down, this is a huge reason to use a flow grid over really anything else that's out there on the market. Its capacity to handle a range of flow effectively is really without compare. We can basically plan on a flow grid with a step drill hole throttle plate to be able to handle flow that's 300 times below its rated max capacity or better. So there's plenty of reason there when you're thinking, hey, I need something that'll handle high flow and low flow. Instead of having to have two different runs, you can use flow grids and get great performance. The range then of what the turn down will be is kind of dictated by what throttle plates that we put in the valve.
Hector asked, if this would fail, does it fail open or close?
Okay, great question. The answer is, it depends. Okay, and I want to get into that more detail too. And this comes up a lot when flow grids are being spec'd, as to, we want, like the worker, maybe to, like you do on a control valve, we want it to fail last position or fail open, and we want the monitor, which is our last line of defense, to fail close. Well, we can't dictate that in a flow grid situation. I can tell you this, that the valve has to basically unload on the gas that's on top of this spring case to open. So it's an unloading design. And typically when you see a situation like that, when it fails to be able to fail close, it's because you have a problem with either the diaphragm having so much wear, or there's debris between the throttle plate and the diaphragm that failed to allow it to fully fail closed or shut off. And also the little plug and stem assembly inside the pilot. If it gets debris, wear, something that's preventing it to seat on the orifice, it will allow gas to dump off the top of the spring case, and it will also then fail partially open. So most of the time, if it fails in kind of a partially open state, but it's trying to be closed. Does that help answer it? And I should say this. Okay, so I'll give you a scenario of fail open, fail close with just one component. So here's a diaphragm inside of this valve. Okay, the way that it's functioning is it's sitting down in this spring case on top of that throttle plate and keeping the gas that wants to cross through the throttle plate, it's keeping it from being able to do that. Now, let's say that this valve was just put in, just commissioned, and there's a bunch of steel shavings, well slag, whatever, that as soon as that pressure comes blowing through, some of it gets through the throttle plate, strikes the diaphragm at such a high velocity that it puts a pinhole in the inlet side of the diaphragm. If that happened, if I had a puncture on the inlet side of this wall of the throttle plate, it would send gas into that upper chamber, even when the pilot was trying to say to the valve, you got to open, the downstream pressure is dropping. It will reload through this artificial hole on the inlet side, and the valve will stay closed. It'll fail closed. Let's take the other scenario. The valve has got all that trash blowing through for a long period of time, and it wears the downstream edge of this diaphragm here, where it's throttling on this throttle plate. So that wear gets so bad that it doesn't seal off when the pilot says shut off, the downstream pressure's reached its set point. I need you to not let anything more off the diaphragm. Well, the gas will creep through anyway, and in that instance, it's going to fail partially open. So same diaphragm, same component, two different scenarios, and it failed different ways. The most likely one is the second one, right? I mean, so you go so long and you get problems with debris or wear on that downstream side, it could cause you to pick it up when it doesn't lock up where it's supposed to. And I'll go into some other scenarios where we do troubleshooting if you like, but there is no clear-cut answer. Okay. All right. So on with just the basic specifications then. We can get, by the way, a higher downstream set point, either if it's functioning as a relief or as a regulator, if we put a different pilot on this. We put a Becker FEP pilot on it, which is basically a pilot for control valves or that style. I can go up to the full rated pressure of the body. If it's got 600 class connections on it, I could set a set point, all the way up into the, 1450, 1480 range if I had that other pilot. I've personally never sold a valve that somebody wanted that, but it's certainly a capability. Okay. All right. So the next thing I wanted to talk to you about is basically, we talked about this a little bit just now with this whole description of failing. how the valve works, and then get into just really basically like what its capability is from a capacity perspective. Okay, so the body itself, and this, I'll use this 1-inch FG11 as an example. But bear in mind, in all these cases, one of the big draws of why a flow grid is really a technician's dream valve is because there's so few parts. It's very easy to maintain. It does a really good job without a lot of TLC, and it's also very convertible. It's like having an erector set or a bunch of Legos. We can change what it does just by adding or removing basic components to the body. We can add a noise trim. We can put on a slam shut controller. We can just do so many things to basically start out with a body that is just a bidirectional. There's no directional arrow on it at all on any of them. And so everything that it's going to do is going to be starting from that start point. I'm going to control gas from one side, trying to cross over a wall to the other. And like I said, they're all rated to the same pressure rating. The only difference is going to be what connections I decide to use on it. Okay, so I have this body. It's trying to perform this function of controlling gas that's crossing to the downstream side. So in order to have all that take place in the way I want, I need some kind of a way to set the capacity, which is happening in the throttle plate. I need a flexible element, which is basically going to control this in a way that allows me to have that real high turn down, and also aided by a mainspring that's an accordion style that allows that peel away kind of function instead of a lift and plug and stem on an orifice kind of function, which inherently has very low turn down, because once it comes off, you're getting gas through. And in this case, you're getting just gas through maybe on the first row of a throttle plate, that kind of thing. So the throttling functions occurring, the flexible element as far as what material I use is going to have a play in how long that material is going to last under those conditions, how well it's going to lift under the pressure differential, and those kind of things. So those are things that I have to consider in the body: the end connections, the throttle plate, the diaphragm. Now I get to how this body is being controlled, because it's kind of a master blaster scenario. I have to have a pilot, and it's not a pilot like the typical like downstream pilots where it's in the vent of the regulator and it's boosting the downstream pressure and it acts like an assist to the mainspring. And in those cases, they're not really they're not responsive. You don't use them in boilers and generators and short run systems because they dull the effect of the responsiveness of the valve, if anything. This is a very different story. This is the brain of this. This is a master blaster situation where the small changes that are occurring inside this pilot are going to result in this, major flow changes in the body of it, the muscle of it. So I need the pilot to be able to tell the valve what to do. If it wasn't there, then, and let's say these holes were plugged, then what it would end up happening is, like, if I plug both of these ports and put it in line, it would just fail open. There'd be nothing that would be loading on top of the valve to actually keep the gas from the inlet side from crossing over that wall under the diaphragm and going downstream. So I have to have the pilot to tell it, first of all, to load the gas on top to set up the initial shut off scenario, and then to dump it and reload it when it wants the valve to open or close. The other thing it has to have is a restrictor. So the restrictor, without that restrictor, the gas would come from the inlet side through this pilot filter, straight through the pilot and load on top. And when the pilot decided, okay, I want to get rid of that gas, I want to dump that gas through the outlet and open the valve, it couldn't do it because the gas that it's dumping through the outlet here is going to be reloaded on top just as fast. So it has to have essentially this little valve, this little restrictor valve, to make the reloading occur slower than the pilot's dumping it off to the downstream, so the valve will open. So to make a flow grid, you have to have the body with the right components for the capacity and the conditions. You need a pilot with the right spring range to set your downstream set point, and you need a restrictor. The way this stuff gets mounted, there's a lot of creativity that can happen there, but the standard is the C mounting, they call it. It's the side mounting, where you put the pilot in the outlet of the body, and you put the pilot filter in the inlet of the body, and you feed the pilot that the small spaces of the pilot filtered gas, so you know, trash can't get in there and mess up the brain. Okay. There can be other things that, like I said, get added to this basic suite of things, but when we call it a model number, it tells me everything about that particular flow grid with those components on it. So this model is an FG11, an FG29, which calls out that this is a 2-inch large port flow grid with 150 class flange connections, race face connections. And so that will dictate the throttling area and the component by saying it's an FG29. The next thing in the description is the throttle plate. So if I'm writing out the description of a flow grid, you know, I'm going to get rid of this stuff now.
While you're doing that, we got another question from Hector.
Yeah.
I might unmute him to ask.
Oh, yeah.
Hector, if you can, unmute you and ask that question.
Yes, good morning.
Morning.
When you first turn on the station, do you turn on the sensing line first or your station first?
What was the question again?
When you're first gonna start the station, right? When you're gonna turn it on, what's the first thing you turn on? Your sensing line or your valves?
Well, first of all, I would never have a valve on my sensing line. And I'll get into more detail about that later, but the proper place to establish your flow through the valve would be just from another weld-a-lead or something like that, and not have a valve on your sense line itself. So, you know, usually it's going to be one of these type of valves, you know, one of these quarter turn like Jomar or Balan valves. And you're going to basically put that in a place maybe where, you know, you have your gauge or something like that, or have it teed, you know, swage lock tee on there, but not on your sense line. So I would have the sense line set up at least 8 to 10 pipe diameters downstream of the exit. And when I introduce gas, I'll want to have opened up a way for the gas basically to flow through, so that I can see that the valve is shut off when I introduce inlet pressure. So I'll introduce inlet pressure, and if I've got my pilot backed all the way out so that it's not forcing the plug and stem assembly inside the valve to come off its seat, only thing that's going to be happening here is the inlet pressure is going to be loaded on top. So when I open that valve, there should be nothing coming out of it. You know, I can soap it. I should have nothing coming through there. It should be bubble tight shut off. So that's the first thing I'm going to do, quite frankly, is I'm going to make sure that the valve is completely shut off when I don't want it flowing. And that way I know when I go to the next stage, which is I'm going to set the valve and I'm going to expect it to lock up at its set point and hold it there. Well, it's never going to lock up if it couldn't shut off. So I'm going to save myself a lot of worry and trouble and heartache by checking for that first. And that way, when I get to my set point, when I run this in, I'm checking my gauge, and you know, I get it stable at my given set point. You know, when I stop my artificial flow, you know, that I've got between my inlet and before I open up this, you know, the downstream system to feed it, I should be able to see it, not let any more pressure through that section of the line, it should hold that pressure and not creep up. Does that answer your question?
Yes, sir. So it'll be a sensing line, inlet pressure, and outlet pressure, correct?
Yes. Yes.
Okay, perfect.
Yes. And that same format, if we're doing worker monitors, it's going to be check for shut off on the worker. Let's say the worker's downstream, doesn't matter though. Check for shut off on the worker. And then I'm going to basically want to do the same thing on my monitor. So in order to do that, because the monitor sense line is downstream, I'm going to basically fail my monitor closed. I'm going to now fail my worker all the way open since I checked it for shut off. I'm going to set it last. So I check it for shut off first, then I check the monitor for shut off, then I set the monitor, then I set the worker, and that's the order there. So let's say again, if I had two valves, say it's these two valves, and both their sense lines are run downstream in a worker monitor scenario, then, and this is my worker. In order to start this process that we just talked about, first thing I have to do is fail my monitor open so I can get my inlet pressure gas to come through to this valve, my worker. And I'm going to have it backed all the way out so I can make sure I get that bubble tight shut off on my worker. Then I go back to this one and I'm going to back it all the way out now, and I'm going to get it ready to be checked for bubble tight shut off. And I fail this one open. Now I should have inlet pressure gas up to it, but I shouldn't see anything coming through this open valve downstream of it and showing up on that valve I've got open. It should be bubble tight shut off. So now I know this one's good to go. And now I can start to set it. So I can set this one now. Let's say I'm got 200 pounds on the inlet. I'm setting it to 50. I run that to 50 on my monitor. And now I come back to the worker, which I've got basically run all the way in to fail it open, and I start backing it out. Let's say my set point on my worker, it's going to be 45. So I basically will back that out until I start to see the pressure on that gauge drop to the 45 point, and I know the worker's taken over. And I've done everything I want to do on this set. I've checked them both for bubble tight shut off before I ever asked them to control anything. I set my monitor first because if I don't do that, then I'm going to be diddling with some artificial way to try to set the monitor around the worker. So now I'm going to have to fail the worker in order to get the monitor set. So this is a much cleaner way. Does that make sense?
Yes, it does. Thank you, sir.
You're very welcome. Okay, so talking about the description then, like when you look at a Mooney model, it always has the body information first. And I said this part, FT29, calls out the size of the throttling area and the size and type of flange connections in the body. So 2-inch large port with 150 class race face flange connections is an FT29. The next part of that is the throttle plate, 100% capacity throttle plate. It'll say drill hole if it has that special design of the throttle plate we're going to get into. And then the type of diaphragm. And if it doesn't have a B here, it's assumed it's nitrile. Okay. The next thing is your pilot. This will call out the same kind of thing, the material of the pilot and its spring range. So if I said this was an FP7, it would mean that it's a brass Series 20 pilot with a blue spring, 25 to 90 PSI. Okay. The next thing in the series is the type of restrictor. This one here is a stainless steel type 24 restrictor, so it's a 24S. We have also a wash steel type that is available. It's just a type 24. The next thing is if it has a pilot filter, that's listed. So that's a type 30 stainless steel with a drain, so 30 SD. And then the mounting, the fact that it's side mounted, the components are side mounted. Compared to, say, this valve, can you pan that over, Drew? So this is what they would call type A mounted with a pilot on top. And this also, this particular one has a gauge mounted so that if you wanted to, you could utilize that gauge to see when the pilot filter is dirty and also when the valve is open, and see how fast it's getting back to inlet pressure. So you can look at responsiveness if you have a gauge there. Again, it's not something that's particularly popular in sales. We certainly can do that, but I really am pointing at this from the perspective of where the pilot is mounted, and this is the top mounted type. We, by and large, see way more people utilizing the side mounted, because literally to get into this valve, all I have to do maintenance is take off the loading line, take off the bolts to the spring case, the cap screws, and I'm in to do my maintenance. I don't have to take off, I don't have to detach the sense line, I don't have to mess with the outlet, I don't have to mess with the inlet line. I have 3 lines to take off to get the pilot and everything with it off of that valve to do maintenance. This makes much more sense, and unless you are not using a body mounted pilot filter like that, one of the benefits of that would be to do it to save real estate on the side of the valve. Like say you got, things kind of close to the run, and it's kind of constricting where you have space to mount your components or to do maintenance on them. And it might make sense to have a top mounted pilot, but if the pilot filter is on the side anyway, you're not really saving much. Doesn't mean that pilot filter has to be there or even has to be one. Highly recommend it, but you could use a filter that's, say, pole mounted, a Welker filter that's pole mounted near the site, and you could run the tubing in a way that gets you around those constrictions, and you can use that A mounted to your advantage. Okay, so to do my maintenance now, it's as easy as this to get into the valve, and when I'm done rebuilding it, I just reattach my my one loading line, and I'm done. So that's the nice thing about that. So most of the time you'll see like the recommended configuration being that C mounted. Any questions on any of that? Okay, so we talked about these bodies and how they're bidirectional. And I have obviously the ports on the body here already hooked in, but on this one, what is going to determine which is the inlet and which is the outlet ports, such as if I want to do a left-hand run and a right-hand run side by side, will be what I put on top of it, and specifically the direction of the spring case. The direction of the spring case will really set the direction of the valve. When I decide that, then I've got the way to put it in. Okay, so the first thing besides the body then that we have to consider in the whole build of the body is this style of an O-ring. And might come up, what about like maintenance on these? How often do I change the soft goods? How often is it necessary? I know a lot of companies have their own internal policies, and it wouldn't obviously be right of me to dictate anything that is outside of those. But what the engineers at Mooney and now Baker Hughes indicate is they suggest an annual inspection and then a change of the soft goods as needed. So it really falls onto the expertise of the technician, the trained person that is keeping the system alive and working well and healthy to decide those things. So with the first soft good component that you might be deciding go or stay, really looking at is it lost its flexibility? Is it lost its ability to basically be compressed by being put into the body, and then to press against that pressure to keep the gas from flowing out where we don't want it to go. We want it to go over that wall and through the valve and not out around the throttle plate and the body on the sides. So when I put a body O-ring in and I'm inspecting it, I want to make sure that it doesn't have any pinches in it, that it's not stiff and dry and feel like it's lost its flexibility. And also I should be able to run my finger across it, and it should be catching my finger. I mean, if it isn't raised above the surface of that body, it's not going to, when I put a throttle plate down on it and torque it down, it's not going to have any resistance to the gas pushing it out of the way. So that's in general the best way I can describe to you about, what about the soft goods, when I change them, and that kind of thing. Obviously, the thing that's under the most potential wear is the diaphragm itself. And you're always going to see that on the downstream side. It's on the downstream edge of that throttle plate where the control of the valve being open is taking place. So you're going to see, and I have some examples here that I thought we could play with. Let's see if I have one that shows this really well. So here's an example. You can clearly tell that this was the downstream side because of how it was being pressed into the throttle plate, because there was inlet pressure on top of it, but the downstream pressure on the underside of this. So this was my downstream side. Doesn't show really much wear. So when this came out, it probably was, well, they were doing some kind of like routine replacement anyway. But this one looks like it has some life in it. And if I wanted to, if I was concerned about that, I could always flip it over and have a new downstream edge. This upstream edge, all it literally is doing in a flow grid is giving, the diaphragm, when it's sitting down on the inlet side of the throttle plate, a place to seal off. So it's not going to get anywhere as long as it's, not like broken down on that side. You can get a fresh side you can use on the downstream side and not have to replace the diaphragm. Same things apply. I don't want it all dried and cracked out. If I see any evidence that tells me that, it's time for it to come out, it definitely needs to come out. If it sits there for a while, it's probably going to need to be changed anyway. An example of that, you can see how this one has basically got a bubble, a layer formed inside it where it's almost like it's tearing itself apart. If any of y'all are scuba divers, you'll know well the effects of nitrogen that gets into a diver's body because of going under pressure, breathing air and going under pressure. That higher partial pressure of nitrogen in the air basically absorbs into his tissues. And when he comes to the surface, he gets the bends because the nitrogen's trying to get out of the tissues in his body. And it now is at such a differential from where the normal levels are on the surface, it causes the little tiny particles, little tiny gas molecules to find each other and form bigger pockets. And those bigger pockets start to try to get their way out, but they're now too big to actually get out in the normal way, and they actually cause damage. They start blocking things and could cause, block of blood flow to the brain and those kind of things. So what's the solution in a situation like that for a diver? Well, they put them in a recompression chamber, and they basically very slowly, very gradually take that pressure off so that those molecules are caused to shrink, and then they're able to get out in a much more controlled way. Well, with this particular situation, it's evidence of this valve. The system got shut down after it had been operating for a period of time, and the molecules of natural gas, methane, got impregnated in the material. And because it just went from 200 pounds of inlet pressure to nothing and then sat there for a while, it got the bends. Okay, so you get a situation where, and this one's funny because on the downstream side where it already had some wear from being pushed into the throttle plate, it had a drill hole throttle plate, it actually almost like punched a chad out on the downstream side. And that's how it is. That's how the pressure actually escaped that was inside the material. So this one surely failed. What would be the solution in a situation like that? Well, when you do maintenance, it's not going to happen like immediately. So if you just go in, shut down, do your inspection, put this thing back under pressure and go back to operating, it's just like putting the diver back in the recompression chamber. That's not gonna be harmful. But if it sits there for a couple weeks or whatever before this thing actually gets put back in line, you might as well go in a lot of cases, and just change the soft goods, because you're probably gonna find some damage that's been related to living at pressure and then having it take off for a long period of time where the pressure got out. Does that make sense? Some other examples, we were talking about failing. This was clearly the downstream side of this diaphragm. And you can see that sand or some other, like metal shavings, rust, blew through this at such a high level, it ate away the diaphragm, physically ate it away. And so for a while, you can see that, it just started taking material away. But at some point, there was a pinhole that got put in that downstream side. As soon as that happened, this valve failed open, because now I got another path where doesn't matter what the pilot's telling the valve to do, I got another path through that diaphragm that's letting gas off the top. So it's not going to hold the inlet pressure on the inlet side anymore. It's just going to keep flowing through. And even though this was peeled back, it's just going to keep eating that hole away bigger. So it failed, and then it just got worse. In this particular case, because of how damaging the stuff that was blowing through was, it did the same thing to the throttle plate. The stainless steel throttle plate ended up like that. Okay, so you can see the holes in it. So it was enough to even damage that. And it's a rare instance that you'll ever have anything but soft goods ever have to be replaced in a flow grid, unless you're just changing capacities or something. So back to what we're doing. We've got the body. We talked about setting the direction. We put the body O-ring in place. The next thing was, we've got to set down the capacity. And these things come in 4 basic capacities: 100%, 75, 50, and 35%. And they have a CG, a gas sizing ratio, assigned to each one of those capacities so that you can do sizing. They also make some custom plates that if you needed something that was outside of that realm for whatever reason, may be attainable. As an example, in these, there's also a 25% capacity plate, which is very handy, and I'll talk about that here in a minute. But to have a 5th plate in a 2-inch large port, because of what you have to do when you're converting over from standard ports, is a good option. Okay, so this sets my capacity. In this particular case, the capacity is listed 50 SD right there. But once I put this capacity, the throttle plate, down on there, and I put the spacer plate that's going to go around it, and I need one more thing to go down with it, if I can find it. Body O-ring. This one that I'm putting down came out, or is going in, is different than the one I just took out, which is a 100% slotted plate. And I'll show you that too. Okay, so this is what the slotted version looks like in these throttle plates. Just like steel splines or ribs. Okay, and there's no inlet or no outlet. I can put it down either way I want. It doesn't matter. At least in the 1-inch size, the inlet and outlet's the same. This one's full face, by the way, notice. 2-inch and 3-inch. When I get to the 4-inch, 6-inch, and 8-inch versions, and there's no bigger throttle plate than 8-inch, by the way, because remember I mentioned at the beginning that the 12-inch Mooney was a dual port. Well, it's dual 8-inch throttling areas, and the 10-inch dual port Mooney is dual 6-inch. So the body's got 10-inch connections. The throttling areas are 6-inch on that, and on the 12, they're 8. Okay, so when I get to anything 4 inches and bigger, you notice that this design of the throttle plate changes slightly. It has a slight bow to it that the mainspring sits down on, and only one side has the capacity, like in this case, step drill hole to set capacity. The other side, as I mentioned, remember, was simply a place for the diaphragm to sit down on when it's supposed to be shut. So it would be very important when I'm putting this throttle plate back in or getting a new throttle plate to put in its place, to put the throttling component of this throttle plate down on the downstream side where that's occurring. You don't have to worry about it on any of those when it's still slotted, because they take a 100% plate like this, and the way they make it reduce capacity is they they weld bars, restriction bars, to reduce the amount of full capacity that can come through. So in that case, they do it on both sides. So if it's a slotted design of throttle plate, you don't have to worry about when you set it down, which one's the inlet, which one's the outlet. If it has drill hole, then you do. Well, the question will come up then, you know, how do I know which one I need when, right? So, because 100% capacity slotted plate has the same top end capacity of these drill holes. So here's 100% drill hole 2-inch plate, front and back. Here's 100% slotted plate. They both have the top end capacity, the same. Okay, when I put those in this valve, they make its CG, its gas sizing coefficient, 1420, and we'll talk about that here in a second too, what that means. But they both have the top end. What it does change, however, is this one has a turn down, which is double what this one is. Because, and think about it, when the gas first starts to flow to the downstream side, there's a lot more control on the low flow side when I've got the first row of holes exposed compared to when I've got, you know, these splines exposed. It's a lot harder to control the low flow. So it's the low flow end that matters. Most of the time in a 150 class Mooney Flow Grid, you're going to use slotted stuff. They're really the best in low differential for good lockup of that diaphragm. And you really only see these in a 600 class Mooney or in a special application where you need a big range of flow. That's when to get them. They cost more, so it's one of the big cost variances between an FG29 with one throttle plate versus another. Most of the time when you see different prices spec'd on the same valve, it's the throttle plate that's causing the difference in price. So these are more economical. In a 150 class or most 300 class settings, you're using the slotted plates. With the reduced capacity slotted plate that I just showed you, the turn down there becomes 150 to 1. So it's fantastic turn down. It's just not as good as the step drill hole variation. Okay, the lowest turn downs are just a straight up slotted by themselves, no restrictions. That's 50 to 1. So I go from 50 to 1. If I make it drill hole, it comes to 100. If I use the slotted plate, but I start reducing the capacity in certain places on the splines, I can get to 150. And then when I start using the nozzle, see the holes are smaller on the underside than they are on the top side, those nozzles. That gets me to 300 to 1 plus. And the other thing is it reduces the diaphragm wear, because as the gas comes through and goes down into those nozzles, the area of high velocity, which was up against the face of the throttle plate and the diaphragm surface, which was causing that wear, now is pulled down into those nozzles. So I get less wear on the surface of the diaphragm. So it has that added advantage. Another reason why with those real high differential pressures where you get a lot of velocity, they make sense in a 600 class Mooney in any size. And as a matter of fact, in 8-inch, when we talk about it, I don't have an 8-inch throttle plate out here to show you, but in the 8-inch, there is no slotted option. They're all drill hole or step drill hole. So, you know, by the time you get to that point, it's really decided as to what to use. Okay, so I've set my throttle plate down. In this case, I put down a 50% step drill hole plate. I needed that body O-ring. I'm sorry, the spacer O-ring, which now is going to be my seal to keep the gas from escaping the top side of the throttle plate between it and a spacer plate. The spacer plate on a 2-inch large port looks like this. It has a pocket for the throttle plate to sit down in. It has a couple places that allow you to align it so I can get it to sit down and line up with my bolt holes. Now, notice now that I don't have any place to actually see the capacity that was printed on that throttle plate. So when the time comes, I'm going to have to put a brass tag on underneath one of the cap screws so that anybody that's going to deal with this valve knows what that throttle plate capacity is without having to open it up and look at it there. Okay, it was 100 that I took out, so now I'm going to change it to 50 step.
While you're on the capacity tags,
yeah,
David would like to know, can we request or order capacity tags for our old Moonies that are missing?
Yes, absolutely. We stock them, you know, so that's an easy thing. You can just tell us how many you need and we can quote them based on that. Typically, the ones we get are blanks, and so we'll actually stamp in the capacity. So if you want us to do that for you, we can do that and send them to you. If you just want to use, you know, a stamping tool or whatever and have the flexibility to use them however you want, then they can come to you as blanks. That's kind of the way we get them because we want that flexibility. So either way. Any other questions on that? Okay, so we've got the point where I've got a body O-ring down, a throttle plate, a spacer O-ring to make sure that I don't get gas escaping between the throttle plate and my spacer. You might ask, well, what's the spacer for? Because on a 1-inch Mooney, on this size, there is no spacer. It's the only one that doesn't. Well, on a 1-inch, there's enough space, if you will, in the pocket of the spring case to let the diaphragm get off the throttle plate and out of the way and to fully open. That's what this spacer is doing. In the bigger ones, a lot of times it's just a spacer O-ring that fits down so that there's some place to give some depth to this diaphragm pocket. So when it lifts, I've got more place for it to actually go. And so it's actually, when it's shut, then a good clean surface between the throttle plate and the underside of the diaphragm. The next thing then we need to talk about is the diaphragm itself. And I mentioned that there's 5 different materials that I can select to go with the application of the process I want. They come in a very soft 60 durometer. Okay, I don't know, we can see here. Note, I don't know if you can see that. Okay, this right here says 18G, right where my finger is. And this right here says 60N, okay? And you notice it also says 2-inch large port on right above it, across it. Okay, so all that stuff is important. The 2-inch large port is important because there are 2-inch standard port soft goods out there, and they look like this. Okay, the outer dimension is identical. Okay, you could put the standard port in here and it will fit with disastrous results. Okay, because the pocket itself is smaller, it leaves room around the throttle plate area where it won't potentially won't seal off, and so one of the first things to know is you're in the situation where in your system you have standard port 2-inch and you have large port 2-inch, and you've got on your trucks standard port rebuild kits and diaphragms and large port. People got to be really paying attention when they go to rebuild that they don't want to put a standard port diaphragm in a large port Mooney Flow Grid, 2-inch Mooney Flow Grid, because there's room where the gas can get around it and not do what it's supposed to do, and that is force the diaphragm up to get over it. So anyway, back to these numbers. The 60N calls out a soft, flexible material that's really good to get full lift and low differential. Remember what I mentioned about that, you know, I don't want to go below 20 in my pressure cuts, you know, because I'm worried about getting to situations where it won't have enough positive closing bias to stay shut and lock up when it's got a little bit of trash or a little bit of wear or something. So I'm going to use this one when I'm making those really shallow pressure cuts, because it's going to seal good against any kind of anomalies in between the throttle plate and the diaphragm. It's going to give that, you know, that nice soft work around the little you know, little specks of material or whatever. It also is going to flex up higher because it's soft. So you'll see this in situations where I'm making a pressure cut of between 20 and 60 pounds. That's perfect diaphragm for that situation. If I'm making a 400-pound cut though, and I've got those real high velocities, will this work? Probably for a while, but its life will be reduced because it's going to wear a lot faster. You know, it's like tire compound. That soft compound is not going to give you the, you know, the 60,000 mile or 80,000 mile wear that the more wear resistant durometers will do. The workhorse in these is a 75 nitrile, to say 75N. And I won't show you every one of them, but this is the 75N, and it's a little stiffer, a little bit better wear over time. And you'll see this being set anywhere from like typically the 60-pound differential up to maximum differential, which I mentioned in a 2-inch is 800 PSID. So it's fine for any of that, okay? I might though, if I'm making at least a 400-pound cut, use one of the real stiff 80 high durometer diaphragms, because it's going to give a lot better wear resistance with those real high pressure cuts. So you're typically never going to see in a 150 class Mooney an 80 high. If there's an 80 high in a FG29, something's probably not right. In fact, it can cause problems to have that super stiff diaphragm. It actually can get in a situation where it acts like kind of like a surfboard or something in the waves, where instead of opening and closing in a peeling way, it kind of flaps. And you get situations when you open it up that it was causing this accordion style mainspring. Where's my tool? Instead of doing this nice easy flex, because this thing is kind of boarding up and down, it actually starts to break the mainspring because of that violence, that vibration that it causes. So just a word to the wise, there is a limit to the wear resistance and where to use it. You don't want 80 high in 150 class sets where you're at most, you know, making what, you know, 280 pound cut. So use the 75s, or if they're the 60-pound cuts or less, use the 60 Duro. There is another 80 durometer diaphragm I want to mention. It's the 80L. It's kind of a mix in the, you know, the material, the tire compound, that gives you better cold weather flexibility. It's not quite as wear resistant as the 80 high, but if it's gonna be living its life down near freezing, then this is gonna keep that flexibility better than the 80 high. So that's when you might consider that. And the final one, is 75V. So you can see, let's see if you can see the V right there next to the 75. That's a Viton, okay? So this is gonna give you that sour gas resistance, and it's also gonna be good for real hot temperature. Let's say you're using a line heater and you don't turn it off in the summertime, and the temperatures sometimes, you know, can get up to say 170, 180. Well, this is good to 225, so it's not gonna have any problem with the warmer temperature on everything. Where it won't be good is when you're in that sub freezing range. This stuff becomes brittle in that temperature range. So there's a good application for each one of these based on where you're going to put it and what you're doing with it. So in this particular case, I'm going to put in the 75 durometer workhorse, and on we go. Okay, so that just sits down on there. Then I select a mainspring. So the next thing is, I got two options here. A standard mainspring for its body size. And as I go up in body size or down in body size, they all look the stinking same. I mean, so here's a 4-inch. Camera's freaking me out because it's like a mirror. It's the opposite direction I hold it. Okay, there's a 6-inch. Okay, so they just get bigger, but they look the same, and they have nitrile pads on either side, so there's no like top or bottom. When that sits down, we basically align that nitrile pad so that it's like where the throttle plate bridge is, right in the center. And the next thing I'm basically going to do with it is going to help me make sure it's centered, but I want it in the center. And the ones with the blue band like that are low diff. They're less stiff. You know, this one has you know, more resistance, more stiffness than this one's nice and flexible. So why would I use the low diff? In those situations where I want to make sure that 60 duro diaphragm gets full lift off the throttle plate when I want the valve open, so I get all of its capacity through in a low differential situation. Caution with these, usually don't recommend them. You guys have dresser roots meters in your system, I know. You don't typically use the restricting orifice plates with a dresser roots meter because its main purpose is to protect the meter, but it could starve the downstream system. It's like trying to pull the gas through a straw just to keep the meter from being overspun. So the solution in that instance, instead of using a restricting orifice plate that only is interested in protecting the meter and not making sure the system as a whole works well, is to just upsize the body of the meter so you have a bigger measurement chamber and the impellers are moving slower at those higher demand periods. Well, the same thing really with this. Yes, you know, it's a solution where you can make this, you know, much softer and much more flexible, but what you're losing is that closing bias when you want it to shut off. And so you start having lockup problems in those real low diff situations sometimes with this spring, when what you could do instead is stick with this, except that it might not give you as much lift, but go with a bigger throttle plate. So you've got the added capacity. And you're going to get that close, that shut off, that you know, it's going to lock up when you want it to lock up because you're getting that help from that stiffer spring. So usually not us recommending these. I don't see that most of the time it's really necessary. Where it can be good is in situations where you know, it's not in a vital location where if it's like you know, partially open and it's not, you know, not shutting off, you're not really getting as big of a problem of it because it's flowing like all the time. So, you know, it's really not creating a problem most of, you know, in any instance that it's actually functioning. But you pick your mainspring and you set that down. And then the final thing is I use this spring case to set my direction. The spring case has a lip right here. Let's see if I can get that. It's got a deep pocket on one side right here, kind of a wall in the back. That's going to keep that spring from sliding backwards as that tries to lift up on the inlet side. It's going to keep it nice and aligned. Okay. It also is my seating surface for the top side of the diaphragm here. And so when I lay this down and I lay it over the bolt holes, it kind of naturally puts, you know, that mainspring where it's supposed to be. And so if I start that way and I start my cap screws, and of course I had to put my capacity tag on, my 50 SD or whatever, put my capacity tag on so that, you know, people know what size it is. But I'll just start it down like that with each one kind of going down even. And then I'll follow the torque value on the tag here, which is 60 foot-pounds for this one, to basically get it all buttoned up. While we're talking about the tag, there's a lot of information on this tag that you can see. The serial number, the model number, basically the end connections, the ANSI class of those end connections, the differential pressure because of the ANSI class. Remember, it's rated at 1480, but it's saying max is 285. The year it was made, the basically the differential pressure minimum and maximum, and the temperature. You can see 175 max, it's got nitrile in it. And then also the bolt torque specification, 60 foot-pounds or 80 Newton meters. So it gives you all that information on the tag. So when I set this down, and the blind person can put a Mooney Flow Grid together, the loading port is always on the downstream side, and it also has a directional arrow, big heavy directional arrow that's stamped there. So when I put this down that way, my flow now is here, and this is my inlet, and that's my outlet port. If I go to make the left-hand run, all I do is flip this around, and now my pilot's gonna move over to here, my pilot filter to there, because now this is my inlet and that's my outlet, and the flow is this direction. Okay. So we are at 10:25. Let me do one more quick thing, talk about that conversion of a standard port to a large port and complete that. Well, then we'll take a break and then we'll switch over to talking about the pilot. Okay. So remember, this was an FG29 when we took it apart. So let's say when we started out in the field for years, this was what would be called an FG3, a standard port Mooney Flow Grid. Same body, so it was already that, but it would have had, and some of those you still have may have this then, a full face throttle plate like this. Okay, so that full face throttle plate is same body O-ring, would have been set like that on this body, and then I would have had a separate layer, a separate level of spacer plate on that full face throttle plate. So the same spacer O-ring applies, same part number, but it's going in a little pocket on the spacer instead of in a pocket on the round throttle plate. And this is where things get pinched, where the manufacturer oftentimes doesn't take enough time, you know, care, concern, and you get a situation like that where, you know, it got pinched in there because they didn't make sure it was in the track when they put it down. That was a spacer O-ring off a 2-inch. Here, and I keep all these, when we go in and inspect these and build them, I'm pulling them all out and putting new stuff in. If that came from the factory like that and we had reason to, that's a 4-inch body O-ring. If we had reason to get in there and reconfigure for whatever reason, we're also carefully looking for these kind of things, because we feel like we're your best line of defense to get this stuff right. And on the other hand, let's say we never got into a particular valve. You find that you have a pinched O-ring like that in a new regulator, and it came from the factory like that. All you have to do is just tell me about it, and I will immediately send you a new one. I'll deal with them. I'll deal with the factory. There's no such thing as RMAs around here. Okay, so if it came from us, we're going to stand behind it and we'll immediately make it right. All I got to know is, you know, the particulars so that I can basically battle them with it, you know. So I'm going to need to know information, obviously, but that's all. Okay, so I get my body O-ring in place. And you guys might find sometimes with soft goods like this, big O-rings, that in the warm temperatures, they don't want to fit quite right. They're too big, and this one's actually acting that way a little bit. A nice little trick is to put them in the freezer for about 20 minutes, and that will help you to get those things to kind of shrink slightly so that they'll fit in these tracks. So obviously I get my spacer O-ring and my throttle plate down. Now I put the standard port. Yay, standard port. Okay, so it says standard port right there on the face of it. Okay, it also has a date of 14 and it says 60N. Okay, underneath the 14, by the way, while I'm talking about it, it has a G. Okay, that G, basically starting in 2014, they started using a new process to basically fuse the nylon and the Buna, the rubber together so that they would resist that kind of tear apart we talked about earlier. So they're supposed to be 3 times better at resisting that kind of decompression sickness. So it's just a natural thing. That was an upgrade that they made. But if you look at one, you take it out of your regulator and it says, I don't know, 12 and there's no G, or 11 and there's no G. That's what the deal is on it. You can also tell they look duller. You can tell like here's these shiny ones that are so hard to like show you the numbers because they got that sheen off of them. The old style, before they did that process, they're dull. So you can see it easier. This says large port and it has the date, little tiny date, it says 98 right there. So it was made in 1998, 60 duro diaphragm. So it's still flexible. It's been in a situation where it's been, you know, properly maintained. You probably could use it just fine, but it's not going to have the same benefits of that better process. Okay, taking them out, it's kind of the same thing. Just because it says it's made in 2006 doesn't immediately tell you if it's been a situation where like steady state flow, it's not getting a lot of wear because it's not real high velocity gas going through it, that it has to be replaced. It's still your call. But when you do, they'll all say a G on it. You know, they'll all have that better process they were built with. Okay, so the important thing though is I put a standard port diaphragm down, and it fits in that pocket much better than. Oh, and by the way, well, what if I try to put a large port in? Let's go the other way. I got this confusion because on my vehicle I have kits for both. Well, what you're going to find is, yes, it will kind of fit, but when you go to bolt it down, it kind of wants to bubble. So you may be able to get it to go down, but it's not going to fit the spacer right. So you may have a similar problem. This one actually may work for you, depending on the durometer. Probably the 60s probably would work better than the 80 highs, as an example. But it's much more negative to try to use a standard port and the large port because of the not filling the pocket. Okay. Obviously, the solution is don't use the wrong one, but just in case, the one's worse than the other, I think. But I put my standard port diaphragm down, put my mainspring down, and just like before, I've got a spring case. It's labeled stamped standard right there so that you can immediately by the eye see that it's different than the large port. Their outer diameter is the same, but the pocket on the large port's bigger, just like the other things, why we're going to get 20% more capacity out of the valve once we put this down. But we started out with a standard port, and that's the way it was. It was an FG3 when we had this together. And so when I converted over, I'm basically taking 4 parts away. I'm taking the spring case, main spring I can keep, although you get one in the conversion kit. The diaphragm goes. The spacer plate goes, because I'm going to use now one that envelops the throttle plate instead of sitting on top of it. The throttle plate goes. So throttle plate, spacer plate, diaphragm, and spring case were the standard port version. And then when I get my conversion kit, then I put on new throttle plate, new spacer plate, new diaphragm, large port. Again, you get a new mainspring, but you get one with it. And my new large port spring case. And I've now converted a standard port FG3 to an FG29. Now what to do with the capacity, because it's not necessarily good that I just increased. If I kept with the same size throttle plates, I've increased the capacity by about 20%. So the CG, if these were both 100% throttle plates, the CG goes from 1130 to 1420. Well, that may not be ideal if I have a relief that's downstream to protect the system, and it was basically designed to relieve the capacity of the FG3. So the solution is to step down. If I'm only concerned about that, the solution is to step down one rung of the capacity on the throttle plate, and the CG will be almost identical. So at this time, I want to introduce you to a chart, which I can send you, like we were talking about. If you email me, I'll send you. It's a capacity chart. It's a real handy tool. And we're going to look at it here just a second about what I'm talking about. Okay, so zoom in toward the top half. Okay, look, this top half of this chart. So if you look on the body size, going down to 2-inch, the 4th, 5th rows down are standard port and large port, standard and large single port. Okay, so that's the families that we're talking about here with this conversion. Remember I said the 150 class RF flange standard port was an FG3? Well, if you go along that line, you see for the throttle plates, the throttle plate rows that are listed there, it's, go to the top just a second, Drew, to show them the categories. Percent capacity, 35, 50, 75, or 100, remember? And it doesn't matter on this chart, on top end capacity, whether it's drill hole, step drill hole, or slotted, okay? If it's 50, it's 50. Okay, so I've got a 100, so I follow along on the CG, which stands for gas sizing coefficient, and it says 1130. Okay, now we'll go down to the FG29 in the rows below it. And you notice that this, now that I've converted it to a large port and it's an FG29, the CG went up to 1420. Okay, so what does that mean? By the way, this chart, if you want it, all I got to do is let me know and I'll email it to you. But it's really nice for just doing some basic questions to yourself. My set, my regulation is doing something. Let's say as loads have increased over time, it doesn't seem to be keeping up anymore. In peak load periods, the downstream pressure drops. Do I need to change the throttle plate or something? Or do I need to convert it to large port to standard port this time? So it'll be one of those questions. Well, here's the simple gas sizing equation. If we come back to the screen up here. Okay. If you can see over my regulator here, let me get this up. Okay, I've got a little formula up here, simplified gas sizing equation. So there are no charts with a Mooney Flow Grid. You just simply can use this as a guide. If I know the CG, which in the case of that FG3 was 1130 and 1420 was the one when I converted it, and I look at what the conditions are of my set. Let's say that I have 200,000 cubic feet an hour. And I need to convert it to CFH or FCFH to use this formula. And then I have my my inlet pressure. Let's say my inlet pressure is 110 PSI. Okay, I just take my max flow rate divided by my inlet pressure, and it will give me a basic thumb rule of the required CG. So 200,000 divided by 110. Okay, messed up. Okay, the CG is 1818, so I'm actually going to have to go to a larger Mooney. Let me increase the inlet pressure so that I can play with the values that I have and keep it in the ballpark. Let's say 150. At 150 on the inlet. Let's see if that gets us into the game with a 2-inch.
1333.
Oh, okay. Thank you. All right, so it's saying the required CG is 1333. Okay, if I had that instance, and I'm always going to want a safety margin. So this is actually probably a little bit tight. I'm probably going to typically want the valve to be about 80% open, not 100% open during peak periods. And by the way, part of the reason for that is if I've got a maximum flow rate required of 200,000 cubic feet per hour, one of the things that I know is going to be taking place is in that peak hour, I'm going to have, like, here's my 200,000 over a span of an hour. Sometimes it's going to be minute rates that are higher than that. Some of it's going to be lower, maybe. Okay, so I've got to deal with making sure this valve can handle the capacity at the peak minute within that peak hour. So that's why, one of the reasons why I'm having a safety margin here that I want to add in. So 1420 times 0.8 would only be 1136. So typically in this situation, that's kind of where I want to go is I want to have about 1136 as the requirement if I'm going to use a 2-inch Mooney with a 100% plate, so I have adequate safety margin. In this instance, though, it's saying that if I can accept a narrower safety margin, when I convert over from standard port to solve my problem to large port, my problem should go away. Not ideal, but it does have sufficient CG to deal with this hourly max. Okay, so that's how I would use this formula to kind of like just use the CGs in this basic simplified gas sizing equation to say, you know, is this part of my problem, or how do I solve this, make my own, you know, my determination, the solution, without having to go into the details of like some kind of sizing equation. I use the sizing equations all the time, but the reason that I do is for other reasons besides just determining whether the valve will work. So I might want to be concerned about what the noise level would be, you know, or something like that. So that kind of drives me to look at the more into more detail about it. And I'm also, if I'm sizing a relief with it, I want to get into the detail. But if I'm concerned about will it work kind of stuff, this will get me there. Okay, and you can use this matrix, this chart that shows you the CGs for every throttle plate, for every body size, as a tool.
And I just